Hi, can you hear me okay?
Yes.
Okay, great. My name's Melinda Webster. I'm at the Goddard Space Flight Center in the Cryospheric Sciences Laboratory. And I started here in January, and I'm very much an early career scientist jumping into the IARPIC collaboration, Sea Ice team collaboration. So thank you for the warm welcome, and I'm really excited to be here. I'll leave it at that since I'll be giving a talk today to give you a more in-depth description of my background and the current work that we're doing here.
Great. Thank you, Jan and Melinda. Again, welcome. So without further ado, Melinda, why don't you're next on the agenda? Why don't we just roll right into that?
Okay. Let me see if I can share my screen. One moment. Okay, can you see that?
Yes.
Okay, great. Okay, so thanks again for giving me an opportunity to introduce myself and give more background on an ongoing project here at the Goddard Space Flight Center. This project is led by Torsten Marcus with co-Is Alec Petty and Lynette Boisvert. And there are also collaborations with Ron Kwok, Nathan Kurtz, and Ed Blanchard-Rigglesworth. So first, to tell you a little bit more about myself, I am an early career scientist. I started researching sea ice in 2009. I started at the University of Washington working with Ignatius Rigger. This work began with passive microwave sea ice concentrations, trying to develop weather filters for improving the retrieval of sea ice concentrations. And then I switched topics entirely to snow depth on Arctic sea ice. And from there, I switched topics entirely again to melt ponds on sea ice and looking at their seasonal evolution. So had a pretty diverse look at things on sea ice to date. Now I'm at the Goddard Space Flight Center, and I'm continuing to work on snow and sea ice problems. One approach that I really like to do is to synthesize in situ observations with remote sensing data to tell a sea ice story or to get answers to sea ice problems. So today I'm just going to give you a brief overview of our current project, and that is developing a snow depth product for ICESat-2. So I'll begin with that. First, to give you background on why snow is important and hopefully why you should care about snow is that it has several, or it plays several critical roles in the sea ice system. It's an insulating blanket on top of the sea ice in the winter, so it really affects how quickly sea ice grows and how much heat is transferred from the ocean to the atmosphere. It has a very high albedo. It's one of the most reflective surfaces on this planet. So in spring, it shields sea ice from incoming solar radiation, which is a very important thing for sea ice surface melt. I wanted to show this figure because it really captures a lot of the important processes that snow has or that it is involved in and how that affects sea ice. And I'd highly recommend, if you're interested, to go check out Chapter 3 in the book Sea Ice that was written by Matthew Sturm and Rob Mason to learn more. So outside of scientific motivation or science motivation for studying snow, it also has very important remote sensing applications. And the example here is laser altimetry. So satellite missions like ICESat-2 are going to be measuring the surface elevations on top of the sea ice, but that will also include the snow on top of the sea ice. So it's getting the snow surface. Now, to extract sea ice thickness from that measurement, you have to have some knowledge of the snow depth. And if you get that wrong, that error propagates into sea ice thickness retrievals. So this is why we're motivated to come up with the sea ice snow depth product for ICESat-2. Now, what do we know about snow to date? Well, we have this snow climatology that was based on historical measurements from the former Soviet Union's drifting ice stations, the North Pole drifting ice stations. And in the figure in the lower right, I don't know if you can see my mouse or not, these are all the drift tracks of the stations from 1937 and 1991. So it covered a large time span. And these were measurements that were taken year round. So in a study by Steve Warren and others, they compiled these data into a snow climatology that is still very much used today. But what we've learned from recent observations, primarily from Operation Ice Bridge, is that the snow conditions are changing on Arctic sea ice, in particular in the Western Arctic. We found that there's been a decrease in snow on sea ice during the spring season, which is the peak snow depth period of the year. And this has pretty big implications, both for science and for remote sensing applications. So what this shows is that the climatology is no longer representative of contemporary conditions. So this is a sea ice problem. We don't have a climatology that's representative of what it's like now, or what the snow distributions are like now. And we have a very sparse data set to work with. Data are sparse because it's hard to go out year round and take measurements over all of the sea ice. So how do we get this information to apply to ICESat-2? So there are three approaches that can be done. One is treating snow on sea ice as a function of the ice age. So if it's younger, you apply thinner snow. If it's older, you use the climatology, and just using that scaling factor. The second approach is tracking sea ice as it moves around and letting snow accumulate on it, and just tracking how snow accumulates on each ice parcel. And then the last approach is building on these two ideas, and it's what we're doing at Goddard, is building a snow model to produce a snow depth product. So I'll just briefly cover the first two approaches just to give you a feel for what they do and what they look like. Okay, so on the left is that approach of applying the climatology, but scaling it based on the ice age. So if it's very young ice, you take a fraction of the climatology. If it's very old ice, you apply the full climatological value. And the figure on the left is that snow depth distribution from that approach. Now in the middle is the snow depth distribution based on doing that ice parcel tracking, just letting snow accumulate. We're applying reanalysis snowfall data to ice as it tracks along. And the ice tracking information is based on satellite observations. So you can see there are some clear differences between the two approaches, which is shown on the figure on the right. What we see is there's thicker snow in the Eastern Arctic, so those red shades, or thicker snow using the parcel tracking approach, I should say, and thinner snow on old ice using the parcel tracking approach. So, you know, how do you choose which one to use based on these? Because this type of difference will have a large impact on sea ice thickness retrievals from laser altimetry. So I compared these two snow data from the ice mass balance buoys at the Cold Regions Research and Engineering Laboratory. And what I'm showing here is a comparison with a little over 50 buoys between 2003 and 2015 of these two approaches. And the way to interpret these plots is the red lines are showing if the approach is overestimating snow. The blue line is showing if the approach is underestimating snow. So what these results should suggest is that both approaches tend to underestimate snow in midwinter, but overestimate snow in spring. So we still may not be capturing the right snow depth distribution. We're still having a problem here in replicating what the conditions are really like. So what processes are we missing, and how can we do it better? So that's really where we're at now, is we're developing a two-layer snow model based on these results, based on these approaches. We're trying to incorporate snow processes that will have an impact on the snow depth distribution. So on the figure on the left, this is a schematic of our model currently. We're still implementing new parameterizations. But what it has now is a wind packing parameter. So every time it gets windy, the snow cover gets dense. It gets denser over time, which matches the climatology. Another parameter that it includes is snow lost to lead. So during windy conditions, and if there is a lead nearby, you can lose snow into that lead. So we're applying sinks to snow. Now it isn't perfect. We still need to develop our melting scheme. We still need to improve how snow is redistributed when a dynamic event occurs. So when ice comes together and forms a ridge, we need to figure out what the best treatment is for that snow. Does it stay in the ridge or should it go elsewhere? And then we'll also be developing a parameter for rain on snow because there's evidence that that's becoming an increasingly important process in contemporary times. Lastly, we'll be assimilating observations. So this will include Operation Ice Bridge snow depth and other snow depth observations available. So I'm sorry I don't have any concrete results to show you, but think of it as a teaser with more exciting results to come. So with that, thanks for your attention, and I'm happy to answer any questions if you have them.
Thanks, Melinda. That's fascinating work. Do other people have questions before I jump in?
Yes, it's Martin. Could I ask one, please, Jackie?
Yeah, I guess I'll let you go. Go ahead.
Thank you. Thanks, Melinda. Some people have suggested that with the changes occurring in the Arctic basin, that there might be greater potential for flooding and snow ice formation at the top of ice flows at the bottom of the snow cover, although the apparent decline in snow accumulation on the ice would suggest otherwise. But there remains that possibility that at least in some regions, perhaps there might be flooding and snow ice formation, which I didn't see in your diagram of snow processes and variation over time, nor is it in your model. Do you think it's worth considering, even implementing in your model?
Absolutely, and I'll tack that onto the list. But no, it's definitely something that we've considered. And based on what we're seeing with the precipitation data and the ice drift data, we think that that process is concentrated in specific regions like Fram Strait and north of Svalbard. But on a broader scale, the preliminary results suggest that that isn't a widespread phenomenon. But you know, we still need to validate that with more observations. But to get back to your question, yes, it is something that is a consideration that we'll hopefully be able to address in the model. I think the question is how to treat it effectively without just blindly adding something in.
Thanks, Martin. Are there other questions?
Hi, Jackie. This is Sinead. Can you hear me?
We can.
Great.
Go right ahead, Sinead.
Thank you. Thank you. I'll ask a quick question. Thanks, Melinda. This is really exciting. Thanks for the presentation. I actually have two questions. One just sparked by the point that Martin just made, and that is, would you consider developing a similar or maybe slightly augmented model for the Southern Ocean, since we're collecting, if it's to be applied to ICESat-2, we would have data from both poles, both hemispheres. So just a question about that. And then the second question would be with regard to tracking uncertainty. So I think, as you probably know, it's actually the uncertainty in the snow depth that that's what flows down to the uncertainty associated with the derived thickness. So it's not the actual snow depth value itself, but the uncertainty associated with that. So how would that then be tracked through the model? Would there be a way to keep a track of that uncertainty as you're accumulating snow?
Great, yeah, thank you for the questions. Regarding your first question, so can we have a separate model or perhaps the same model that treats the Southern Hemisphere snow cover differently? I would hope so. We haven't discussed that yet, but of course that would be in the future plans long term. We're starting out what I would suggest is the easier case, being the Arctic, because the Antarctic is much more complex in that we don't have a lot of observations on what the snow processes are and how important they are, and just how different, or the different magnitude of the processes by region. So I think long term we could get there, but it's not the immediate next step. Now for your second question on how to track uncertainties, the data assimilation part will be heavily based on the uncertainties of the observations and weighted on those. To track them is a really good suggestions, and something that admittedly I hadn't considered. So I'm making note of that and to share with the rest of the group.
Thanks, Melinda, and Sinead for the questions. Any other questions? I'm going to ask mine. So you talked about data assimilation, which will be a great feature of the model, I guess. I'm wondering then, if you're assimilating this data, what data do you expect to hold out to evaluate the effectiveness of the model?
Right. I think point measurements on a mass can be very valuable for assessing how the model's performing. For example, like the buoy comparisons over a long time period is a really nice way not to validate, but to assess the model. I think taking a point measurement individually doesn't quite give us the information we need. So in a way, taking as many snow surveys that have been done and field campaigns and things like that as our assessment point for the model is the way forward.
Follow-up question, do you have any plans in any of the upcoming ice bridge flights to do any sort of ground truth that might be able to help you with this development?
Oh yeah, I would love that, but currently I don't think there are any plans for snow over sea ice or any plans for validation of snow over sea ice. There may be potential in future campaigns, coordinated campaigns, but I can't really speak to that since I'm not on the science team and they set the recommendations for the science needs.
Good. Well, I hope you'll be talking to them.
Okay, great.
You got
Thank
close
you.
proximity.
That's true.
Great. Any other questions for Melinda? Thanks, Melinda. Well, again, welcome to the team, and that was a great introduction on the work you're doing and further evidence of why you've been asked to join us. So I'm going to